Hi, I'm Itzi Cohen. I'm a PhD student in Alex Rex's group. This is our group, and in this talk I would like to talk about our first project, which is quantum simulation of the Haldane phase with trapped ions. In quantum simulation, we simulate one quantum system with another quantum system, which is easier to control and measure. So in this case, we want to simulate the Haldane phase and our simulator is the trapped ions setup. Our theoretical proposal was published in PRL earlier this year. We collaborate with experimental groups that we want to realize our proposal, both the laser and the microwave design, based design. Where in the laser-based design, we work with Chris Monroe, and in the microwave design, with Winnie and Christoph. We also get DMRG support, which is numerical support from Javier. I will start with some motivation. Until now, we saw quantum simulation of spin 1/2 chain, where we could see in the Ising model the phase transition between the paramagnetic to the ferro or antiferro phases, with the local orders of the ferro order and the antiferro order. Also in the XY and the Heisenberg model, we could see that those local orders decay in a parallel behavior. This is corresponding to a vanishing gap between the ground state to the first excited state in the thermodynamic limit. It means that the spin 1/2 chain is a gapless system. We could see that if we increase the degree of the spin to be larger than 1, much larger than 1, then we just reduce to the trivial interacting harmonic oscillators. However, there is a special case where we have integer spins as opposed to the half integers before. For example, for antiferromagnetic spin 1 chain, Heisenberg chain, spin 1, it means that we have 3 level systems as opposed to 2. Then we obtain the Haldane phase after the guy discovered it in 1983. According to the Haldane conjecture, this system will have a finite gap between the ground state to the first excited state, even in the thermodynamic limit. This is corresponding to exponentially decaying correlation function of the previous local orders. So in the long chains, those local orders are vanishing. They vanish. However, there is another order which survives. This is a non-local string order. The non-locality comes from that fact, the following fact, that if you take a look at the string correlation function, so between I and j we have to calculate or to take into account all the spins that are in between. That's where the non-locality comes from, and that's what makes the Haldane phase a non-local or topological phase in one dimension. So one of the systems that we can find the Haldane phase is the spin 1 XXZ antiferromagnetic chain. The XXZ means that we have the same prefactor of the X, Y, and the difference from the Z, and with the additional control parameter, which is non-interacting term. We can think about the Hamiltonian as a conflict between those two terms. The Ising term here wants to obtain the nil order, antiferromagnetic order, whereas the flip-flop wants to destroy it. So if we take a look at the phase diagram of this Hamiltonian, and we take large lambda, so we are reduced to the Ising model with the antiferromagnetic state or phase. If we take D to be the largest term, then we are reduced to the trivial D phase, which has a trivial ground state, which is 0 in every side. This is a tensor product of zeros. However, the interesting part is here. where all those terms have the same strength. This is the Haldane phase where it can be found. More precisely, in this point, where lambda is 1 and d is 0, this is the Heisenberg point where people have calculated the energy gap, the correlation length, and the spin parameter using DMRG. So in our simulation, the spin is modeled via the hyperfine structure of the terbium ion, where we have the triplet and the singlet. If we take out of the game the 0 of the triplet, we are left with a spin-level system which model the spin 1, which is the spin-level system. By applying two resonant driving fields, like that, we move to the dressed basis, which is in a perpendicular axis, because the up, dark, and down are the eigenstates of the Sx, which is the spin, the projection of the spin over the x-axis. It means that if the polarization axis is in the z direction, so the magnetic field is in the z direction, and also the magnetic noise is in the z direction, then we work in a basis which is perpendicular to it. Then, by using the rotating wave approximation, the magnetic noise is cancelled. This is the continuous version of the dynamical decoupling. So we would like to engineer this Hamiltonian, the XXZ Hamiltonian. It means that we would like to engineer two-body Hamiltonian. To induce spin-spin interaction, we need with trapped ion, we need to use which is carried via the spin-spin interaction is carried via exchanging of a virtual phonon or phonon bus. So we have to use we have to have terms which couple between the spin to a phonon. With laser, this is done. We have this term via the momentum or the lambda parameter, which couple between the phonon and the spin. But with microwaves, which have a very small lambda parameter or small momentum, this cannot be done. However, we can use magnetic gradient and obtain the same result. So in the second perturbation approach, we obtain the flip-flop, which is the XX plus YY Hamiltonian with a residual that goes like SZ, which is coupled to phonon. This is a noisy term for us, but because our ground state that we are going to use, as we describe, I will show later in this presentation, they have vanishing projection over the SZ, then we are decoupled from this term and we don't care about it. To induce the lambda term, we apply a resonant RF between the up and down. This is a trick which I will not get into detail about it, and also to apply to build or to engineer the D term. And we use the following trick. Instead of having the two resonant driving things as before, we detune it in the amount of 2D. So once we build or engineer the Hamiltonian, we would like to simulate the Haldane phase. It means that we would like to obtain the ground state of the Haldane phase and to verify that we are there, to measure it. So we start for that we start with the large D phase, where we know it has a trivial ground state. It's the tensor products of zeros. We start with the ground state and with the large D Hamiltonian, and then we adiabatically lower the D term until we are in the Haldane phase. Adiabatic means that we need to do it slower than the gap, the energy gap. However, in this point here, we cause a second order phase transition, where the gap is closed in the thermodynamic limit. But even not in a thermodynamic limit, then this gap is not closed, but it's very close to be closed. So it's very narrow, and then it means that we have to use a slower adiabatic path. Then, in that case, the T2 time or the decoherence effects or noise effects could limit us and could destroy our results. So for that, to overcome this problem, we add a symmetry breaking perturbation term, which destroys all the symmetries of this Hamiltonian. And by that, we instead of crossing in the phase transition, we just go above it, and we are promised not to cause any phase transition in this path. If we do it adiabatic, we can get the Haldane phase with its ground state. So we have to also use a large T2 time for that. So we have to be robust to the main noise sources. The main noise sources of this problem are the magnetic field, as was explained before. We are decoupled of it by the continuous version of the dynamical decoupling. We are also decoupled from the Rabi frequency fluctuations because the operator that describes it is SZ. And our ground state have vanishing projection over this operator because the ground state of the VD phase is just a 0, 0, 0 in every site, which is trivial. And the ground state of the Haldane phase, according to theoretical papers, has the same amount of same number of occupied sites with up and down. So that's why when this operator operates on them, it's 0. For the same reason, we are decoupled from this residual term, and we can say that we work in the decoherent free subspace, which increase T2 time and enables us to work in even slow adiabatic path. So to sum up, in this project we show how to build this Hamiltonian, the XZ Hamiltonian, where we can find the Haldane phase for both the microwave and laser-based design. We can reach the Haldane phase adiabatically by perturbation, by symmetry breaking perturbation, and by the fact that we are robust to the main noise sources of this problem. Okay, thank you.